Hi there. This video will show using Excel that from a balanced three-phase electrical system, you gain constant power. So what we have with three-phase systems, there are many advantages of three-phase over single phase. For example, you get the same power output with three-phase compared with single phase using less copper. Now that sounds counterintuitive. Three phase, three wire system, single phase, two wire line and neutral. But if you go through the math, and because the voltages are equidistant in phase, 120 degrees apart, you can get the same power with less copper. You also get constant power output with a balanced system that will be demonstrated. Because you get constant power out in the stator of a three-phase motor, you have a naturally rotating magnetic field of constant flux and constant frequency. The frequency is fixed by the electrical supply into the stator. And because you have that rotating magnetic field of constant flux, you can have three-phase motors that are naturally self-starting through electromagnetic induction. Single-phase motors have got more components than three-phase. Three-phase motors are more efficient, they're more robust, and it's actually a simpler design. If we go to a little quick diagram of a three-phase system that's got here, so three-phase system here. So in the final substation, what's typically done is you have 11 kV to 400 volts, three-phase system, final transformer. So what you can do is you've got the option of providing a 400 volts three-phase industrial supply. However, if you connect it in star, such as this diagram here, with a central point, a reference point, which is normally the neutral, you can then pull out three individual lines. And these lines will be at 230 volts compared with the 400 volts between the three lines. So line to neutral in the star will be 230 volts, and that's what occurs in the final substation, so that you can provide 400 volts industrial three-phase supplies, or you can provide standard 230 volt line and neutral 3-pin plugs, line neutral and earth to domestic supplies. And if we go to this final one here, to show in a phasor diagram that we have a factor of the square root of 3, you can do this by phasor diagrams, and you can also do it by adding the numbers in an Excel. How do you add the voltages together? Well, between two lines, if we take this line and that line, the voltage across these two lines, because it's going across two phases or two loads, you have to add the two phase voltages together. However, you need to take into account the direction. If we use the star point as the reference and label the voltage from the star out to this line here, the same for 2, the same for 3. However, to go from this voltage here, from the starting here to this line voltage, we have to add -2 +1 to keep the direction constant, and that is what we'll see through the phasor diagram. So in this phasor diagram here, in this column, we've got the 360-degree rotation through 1 degree step changes. And for each 1 degree, we can plot out our three-phase voltages that are 120 degrees apart. And we can plot them out, which is obviously pretty much instantaneous in Excel with the digital tools. It takes out the tedious manual effort of plotting them step by step, just doing manual calculations. Now we can see the voltages have the same amplitude, which is typical of a three-phase system, but the voltages are 120 degrees out of phase, which is the critical point of a three-phase system, is how you get constant power and how it's an efficient system compared with single phase. So as we talked about previously in terms of creating the line voltage, these three line voltages here are adding two phase voltages together, but you have to take into account the direction. And if you do that with Excel, we can take these three columns here, these three columns here, and we can do in recommended charts. And again, for the line voltages, we can see that the amplitudes are all the same. The amplitudes are all the same. They've got 120-degree phase shift, but the amplitude is not now 230 previous. The amplitude is, excuse me, that's the other one. That was the phase one. It's got 230 volts. If we do another one here and we take the line voltages and we do insert recommended charts with the line voltages, we can see that the line voltage is now at 400 volts. So it's increased. And if you go through the maths, it's increased by a factor of the square root of 3. The square root of 3 comes out of the phasor diagram, but you can also see it in we can see here, there's 230 volts phase voltage, 400 volts line voltage. Between these two amplitudes is a factor of the square root of 3. And you can actually see that from the numbers, and you can also go through the maths and show that as well. What we can also do in here is we can calculate the phase currents. Now, for current is the voltage divided by the resistance in each of the loads. What I'll do is I'll put them back to balanced loads. They've all got 20 ohms here. They've all got 20 ohms. And what we can do is we can work out the phase current, from Ohm's law, V divided by R. So it's the V phase divided by the R in the load. And we can do that for 3 of them. And what we can do is then calculate for each of the phases the power individually. And then what we can do at the end is we can add up all the powers to see if the power is constant or not. Now we can see in this column here that that's not 100 ohm load. We're just adding the 3 powers together. Yeah, we changed the load. If you add the 3 powers, you can see here it comes out to be a constant number. Now it's a constant number as in constant power because we've got the same loads here. However, what happens if you unbalance it, make that 15, let's make that 10. So they're all different loads in here. And what happens to if you add the 3 powers together, then the power is not constant. So let's see that in a graph. If we go back to a graph, we'll select the angle as the reference. We've got that power there. We want that power there. We want that power there. And we also want to add on the sum of the powers. And we want to have a chart to show it visually. What we can see here is we can see that we do not get constant power out of the system. That's the power, the sum of the powers here. And you can actually see, because it's unbalanced, the powers have got different amplitudes. So the powers are always positive, but the powers have got different values, but the power never goes negative. If you minus, you get a plus times plus for voltage times current. The power never goes negative. If you add them together, you will get a constant value if it's a balanced system. So what's going to happen is if we just go back and change the values, which is the beauty of Excel, is you can quickly change parameters, make it a balanced system, balanced load, the power is constant. So we can see that there. Now, if we do a phasor diagram, what we've got and this is for our balanced system here, what we have in this phasor diagram here, what we've got in this phasor diagram here is we've plotted out the 3 phase voltages. There's phase 1, phase 2, phase 3. There's line 1. And line 1 is that phasor there, which is the V1. At the end of V1, we add on to the end of there the negative of V2. And if you go to the end point, it's that line there. It is that line there. So we can see that three-phase voltages are the equal amplitude. The line voltages have got equal amplitude here as well. If we go back to here and we unbalance our system, just put in our values, unbalance our system, that doesn't affect the voltage phasor because we're not changing the voltage, we're changing the currents because current equals voltage divided by resistance. So we've changed the R, not the V. So if we plot out our three-phase currents and we add them together, that little phasor there is the addition of the three-phase currents. Now, in a balanced system, we want that to be zero, and that's why you don't necessarily need a fourth wire from the start point. You can have a three-wire system because in a balanced system, the currents add up to be zero. Because this figures that I put in, the system is not balanced, then you do get, if you add the three currents together, then you do get a current for the sum, which in this case is 3.3 amps. If we go back to here and I make my system balanced, it doesn't matter what the numbers are. Let's make them all 17. Yeah, balance the loads up so they're all the same value. Go back to our phasor diagram. Indeed, go back to here. It's updated so we get constant power. We go back to our phasor diagram and what we could see is now is if you add the three phase currents, or indeed in a star system, the phase current and the line current are physically the same thing, physically the same quantity. If you add them up, they come to be zero. So how do you add up 13.5, 13.5, 13.5? It's an addition, it's a two-dimensional computation, it's size and phase. So with size and phase, because they've got the same amplitude, equidistant, the sum of the currents is then zero. If you just go back here just to prove it, if you unbalance the system, let's just unbalance that, unbalance it, you can now see that we don't get constant power. The powers are all different from that diagram there. Phasor diagram, it doesn't affect the voltage phasor diagram. That's still the same because we haven't changed the voltages, we've changed the current. And we can see in this line now that we've now got the addition of the currents is now out of balance. And if you add those three currents together, it's now up to 6.7 amps. That's an unbalanced system. So the ideal is a balanced system with the loads being equal. Now, in a physical system, that's obviously quite difficult to do. But that is the intention of having a balanced system. So we'll just go back to balance. It doesn't matter what the number is. We'll just do 11 just to show that, excuse me, that the actual number is not important. It's the fact that they're all the same. Constant power out of three-phase system. And if you add the three currents together, they cancel each other out. You get zero. Thank you for watching. Please, any comments below, please subscribe.